2 of the molecular momentum transfer. Okay, so we are here on the second main topic. So last week we learned about, we recap back a bit on what is momentum flux, right? Or another term for it is the shear stress, which is equivalent to force per unit area, right? And then for, let's say, if it's Newtonian fluid, then it should obey the Newtonian law of viscosity, which is equivalent to negative mu, which is the viscosity, and then multiplied to the shear rate. So let's say if it's for the case for a flow, that is in x direction, right? And then where the momentum is transferred through a plane that is perpendicular to the y direction. This refers to the plane. All right, so that's why if you look at the shear rate, this shear rate here is expressed as the rate of change of velocity in the y direction, because the velocity would then vary in the y direction. Okay, so just a quick recap back of what we have covered in week 2. Yeah, so and for liquid we have different viscosity, and for that we can categorize into Newtonian and non-Newtonian fluid. So if you recall back, for non-Newtonian fluid we have the Bingham plastic, which need a yield stress in order to initiate the flow. And then we have the pseudoplastic fluid, which is also known as the shear thinning fluid, right? And the dilatant fluid is also known as the shear thickening fluid. Okay, and for Newtonian fluid is where the fluid, it has a linear relationship, right? The linear relationship between the shear stress and the shear rate, whereas non-Newtonian fluid, it doesn't have the linear relationship. And for the non-Newtonian fluid, it can also be categorized into two types, right? The time dependent and time independent. So for time dependent, we have the thixotropic fluid and also the rheopatic fluid. For thixotropic, you can see that it undergoes reversible decrease in the shear stress at constant shear rate. So the rheopatic, it would then be an opposite of it. All right. So after that, we also discussed about the Reynolds number, Prandtl number, Nusselt number, and Biot number, which these three we will be using quite often in this module, right? So especially for Reynolds number to categorize whether it's a laminar or a turbulent flow. So these two we'll learn it later, right? When we are going to use some correlation to solve for the convective heat transfer coefficient. This will be in later chapter. All right. So basically that's what we covered last week. We also talked about what are the methods, right? The power law method and also the friction factor method to solve the pressure drop. Right, so that one we have done a mind map. So in case if anyone needs the tutorial class on last Tuesday, right? So we did a mind map on how to determine, right? So which method to use. All right. So so if you missed that one, please check with your friend, all right, and get a screenshot. I think some of them get a screenshot. All right. So you check with your friend and get the picture from your friend. All right. So now, as for today, as mentioned last week, right? So this week onwards, you'll learn about how to formulate the velocity profile. It will be quite challenging, so make sure you pay attention. Okay. So for today, we are going to talk about the velocity profile. So you have been introduced to it a little bit. So today we'll talk about it more in that, and then we'll look at the flow conditions. So this will be for the first hour, we'll be covering this one. All right, then on the second hour, so we'll discuss about when to use the overall momentum balance and then when to use the shell balance. All right, so now, which means actually for the topic that we are going to discuss today, it actually mapped to the two learning outcome. So the most important one is you need to master how to formulate the velocity profile using the shell momentum balance method. Okay, so now because for this one, for formulating the velocity profile, oh yeah, thanks for reminding. Let me it's okay, I'm going to upload the pre-recorded version so that it's more systematic. All right, so for every lecture I'm actually uploading the pre-recorded section, right? No worries. Okay, so for velocity profile we actually have two methods to solve it. One, which is what we are going to cover today, which is the shell balance method. All right, and then another one, we'll learn it in later weeks, which we call it the Navier-Stokes equation. So Navier-Stokes equation. So this one would be more challenging because you are going to learn how to formulate from scratch. So like analyzing what are the forces that involve, and then for each of the forces, the student will then need to write out the equation themselves. So this would be quite challenging, right? Whereas for Navier-Stokes equation, there's a equation that is ready already, where the student just need to analyze the flow condition and then uh, assume some terms to be negligible, then you can proceed to solve the differential equation. That's what this one, Navier-Stokes equation. But this one is the most challenging one that we are going to cover today, to learn how to formulate velocity profile from scratch. So after getting the equation to describe the velocity profile, then the students should be able to analyze the flow behavior. All right, how the velocity change from certain distance from the wall, for example, how the shear stress, it varies at certain distance. So that's why here I put that for today's topic, it actually aligned to these two learning outcome. All right. So now, okay. Now let's look at the first part of our today lecture. We are going to talk about the velocity profile first. Then we'll look at the flow conditions. So now, what is a velocity profile? So velocity profile is actually a diagram. So something like this. This our velocity profile, right? That shows us how the velocity varies in a certain geometry. And you can see that there are different shape of velocity profile here, right? So what does it mean? So here, if let's say if this is the case where you have a pipe flow, right? And then this pipe here, it has a radius r. All right. So when the fluid first enter the pipe, so at this region here, okay, this region here that I'm going to highlight, all right, this region here, it enter at a uniform velocity. Let's say v naught. All right, so you can see that the velocity is of the same magnitude when it first enter the pipe, right? So it enters at a uniform velocity, but when it's further down the pipe, so let's say this is the positive x direction. When the fluid flows further down the pipe in positive x direction, you can see that the velocity profile here is start to change, right? And at the same time, if you look at here, the velocity boundary layer, it starts to develop as well, right? So this region here, right? This one, this one, this is the the velocity boundary layer. It start to develop. These are the velocity boundary layer. So why do we observe this kind of change in the velocity profile? As mentioned last week, right? So when the fluid first come into contact with the pipe wall, so especially at this region here, when at r equals to the radius of the pipe wall, the velocity, it will comes to a stop. V equals to 0 because of the no slip condition, right? That's where also because of the friction to fluid flow, right? That caused by the pipe wall, so that it comes to a stop. All right. So where here, if we are going to write okay, this is velocity in x direction, and then here it will be the flow in x direction, right? Where the plane is actually perpendicular to the radial direction, right? So it's tau rx, where at this point here at the pipe wall, the shear stress, it would be the maximum. All right. Okay. So now when the fluid travels further down this pipe here, the viscous effect, it starts to be significant. So that's why you can see that the velocity start to change, right? So it almost 0 here, then it's slightly increased beyond zero, right? Then when it comes to the center of the pipe, right, the point of symmetry, the center of the pipe here, when r is equals to 0, that's where the region here, okay, let me mark it. All right, when r is equals to 0, that's where your velocity x, it will almost approach the maximum velocity, while the shear stress is equals to 0, which is, we call it this one here. Okay, so if I'm going to highlight it, so this region here that you see is what we call the region of inviscid flow. This is the inviscid flow region, all right, where the viscous effect is negligible. Okay, viscous effect is negligible, or you can say that it's insignificant in this section here. So you can see that when it's closer to the pipe, the viscous effect is more significant until this region here. All right, so you can see this region here. All right, so the velocity profile, it starts to become more developed. It's more developed really in this region, which this region here, if you look at it, we call it as the, okay, hold on here. Okay, which this region we call it as the fully developed region, in which when in the fully developed region, so the velocity profile is established already. Velocity profile, right? The velocity profile, it will become unchanged. It will remain in this shape here, because here the velocity in this region, the fully developed region. So let's say if I'm going to denote here as V1 at this point, all right, and then somewhere here at the end of the fully developed region as V2. So in this region, V1 will be equals to V2. So your velocity at any section of the pipe, it will be constant. So maybe at this point here, the velocity, it will be, so let's say I denote V prime 1. So it would be smaller than V1, right, because of the viscous effect. So does this one, V prime, let's say V2 prime, it will be smaller than V2, right? But in the fully developed region, your V prime 1, it will be equals to V2 prime, right? So which means now in the fully developed region, all right, so your velocity, it will no longer be affected by this one, the entrance effect or the exit effect, all right? So it's fully developed now. Okay, so which you can see that the velocity boundary layer, it also start to merge here at the this one, the start of the fully developed region. Whereas this region here, right, at the entrance, near the entrance of the pipe, they call it as the hydrodynamic entrance region, which you can see that most of the velocity profile, this one and this one, right, it changes with the length, right? The length, the distance from the entrance of the pipe. So in this region, the Vx, the velocity, it depends also on the distance of the pipe. All right. Okay. So this is the case if it's for pipe flow, right? Flow in cylindrical pipe. So what happens? Okay, that will be later. All right. So let me show you also. So this is the case if, let's say, if we have laminar flow, right? Laminar flow, where you can see that the velocity profile, it has a parabolic shape, right? It has a parabolic shape. So later we'll derive, all right, formulate the velocity profile, the equation, and you see that the equation is, you have a square term for it. That's why it's in a parabolic shape here. All right. So the arrow shows in this direction is just to describe, right, to illustrate how the magnitude of the velocity. So when it's even longer, which means the velocity is even higher, right? So that's why you see at the point which is near to this one, the pipe wall, right? This one here. So it's stopped at this point here because the velocity is 0, which means the magnitude is the lowest. All right. So now, so that's the case of if we have a laminar flow. So if you look at this diagram here on the next slide, right? So this is where you have a laminar flow, right? Where the velocity varies from the distance of pipe. But if you look at turbulent flow, you notice that there would be a region that is flatter, right? It is still parabolic, but this region here is flatter, right? So because in turbulent flow, you can imagine here, all right, at almost near to the center of pipe, all right, so you have a lot of mixing, right? So in turbulent flow, you have eddies, you have mixing, so which means there's a lot of mixing in this case, so which means your velocity gradient here, it will be smaller, right? It will be smaller. The velocity gradient, it will be smaller. So in that case, which means the variation in velocity in this region here, it will be smaller as well. So that's why you have a flatter parabolic shaped curve, right? Which you can also observe here, right? So we have turbulent flow, but depends on whether it's a smooth pipe. So if it's a smooth pipe, you can notice here, the curve, it would be even flatter, right? So in this region here is even flatter. Whereas if it's a rough pipe, right? So because if it's rough pipe, which means the friction effect or the shear stress, it will be more significant. So that's why you can see that this one here, it has, the curve is more significant in this region here, right? Because there would be lesser mixing if the pipe is even rough. All right. So this is the case if we are looking at pipe flow. Now, if let's say if we look at flow past a flat plate, So this is, let's say if we have flow past a flat plate, so where you have a plate here, so when the fluid first come into contact with the plate, right? So same thing, it will enter at a uniform velocity. So let's say here they denote it as u infinity. All right. So then, so actually, if you look at it, so you have a flurm of fluid like this, a flurm of fluid in this region, but the velocity boundary, the boundary layer, it will develops in this region here. This is the velocity boundary layer. So which means this area here is actually the inviscid flow region, right? Where the viscous effect is not significant yet, right? Because it's quite far away from the plate. So when the fluids first come into contact with the plate, so you can see that it first flow in a streamlined manner here within the velocity boundary layer, and because of this, so you can see that the velocity boundary layer, this one, the velocity profile, it looks here, right? The gradient is more significant in this region here. Okay, let me highlight it. This region here is more significant as compared when the fluid flow further down the plate, right? So you have a transition region here that you can see. This is a transition region where sometimes the fluid, it will flow in streamlined manner, or sometimes there will be some mixing, or sometimes it could be both, right? So then even further down, all right, in positive x direction, when the fluid flows in further down positive x direction, then the turbulent region is more developed already. So there is more mixing of fluid, more eddies that bring the parcel of fluid from here, from more high velocity region towards the lower velocity region. So that's why if you look at here, this section here, okay, let me see how I can highlight this. Okay, this region. All right, so you can see that for this velocity profile, right, the curve in this region, when the turbulent flow occurs, the gradient of the velocity profile is almost flat because there's a lot of mixing. Velocity gradient is very small in this region. All right, so here you can see, all right, so the comparison between the velocity profile for laminar flow. So this is the one which is for laminar flow, right? So you can see that the gradient of it is more significant as compared to this one for turbulent flow. Initially, there's some velocity gradient because some, as you can see here, some of the fluid that is close to the wall, right, the plate here, it's still flowing in the streamlined manner because of the viscous effect, shear stress, right? What resistant to flow, we call it the resistant to flow. So that's why you still have velocity gradient, very significant velocity gradient in this region here. But as it's further away, so let's say this is the y direction, right? So at a distance further away from the plate, so let's say y equals here, y equals to delta, all right? So your velocity gradient is insignificant, and then it becomes flatter already. So which, if you recall back when you learned last time, right, when it's y almost near to y equals to delta, usually the velocity in x direction, it will be almost equals to 0.99 of the free stream velocity. All right, okay. So before I move on to the next to talk about the flow condition, so do you have any question about the velocity profile now? Any question? You can put it in the chat area. Any question, anyone? If it's all good, perhaps you can help to give a thumbs up so that I can confirm that we can proceed. Okay, great. Okay, great. So that's the difference between the velocity profile for laminar flow and turbulent flow, right? So if it's more curved, which means you have a very great velocity gradient, right? When it's the curve, right, is not, the gradient of it is not that significant, which means the flow is of very high velocity, or it's almost turbulent flow. Okay, now, so for today, most of the things that we'll discuss, right, is because the velocity profile, it will also be affected by the geometry, as what you can see just now when we have pipe flow and when we have the plate. All right, so for the lecture today, right, so we are going to look at the flow condition for two types of flow. If we have a pipe flow, and we are focusing on laminar flow, right? And then for also 4 pass a vertical plate. So what we look at just now is a horizontal plate. So what if it's vertical plate? So how does the velocity profile looks like? It will still looks something like this. So we are going to talk about it. So first one, let's just look at the case of pipe flow, right? So there are quite a few of slides in this subtopic here, but actually you just need to refer to the summary slide. But I'll go through each of it one by one, right? So that you're aware of the things that you need to be alert of. All right. So let's say if we look at pipe flow, where the case if we have a laminar flow and then it's one-dimensional. It's a one-dimensional laminar pipe flow. So one-dimensional. Why I mentioned one-dimensional? So which means here we are focusing the flow of the fluid in x direction. The flow, okay, fluid flow in x direction. So when fluid flow in the x direction in a pipe, so this is a 2D diagram. So if it's a 3D one, you can imagine it something like this, right? So if it's a 3D one, right? So now what happens is, all right, so as you know that we have covered last week, right? So let's say if we have a pipe here which is of radius, right? It have a linear radius of big R, right? Capital letter R. Okay, here we denote this region here. All right, so at the center of pipe as R equals to 0. Usually that's how we illustrate it. All right, then at this pipe wall here, you can denote that boundary as R equals to the big R. All right, so now, so when the fluid flows into the pipe, all right, so if we are analyzing this fully developed region, right, so now from now onwards, when we discuss about the velocity profile, we are talking about the fully developed region, not the entrance, right? Not the section close to the entrance or the exit. Those section, your velocity profile is changing with distance, but we are looking at the fully developed region where your velocity it will be it will remain constant at any along that particular distance from the pipe wall. All right, so it will not change. All right, okay. So now at r equals to 0, as mentioned, that's where you know that the shear stress, right? So it's tau rx is almost equals to 0 because the viscous effect, right, is negligible, right? And this is the region also. The Vx it will be equals to Vx max. All right, and then here, which is the section where you have the maximum shear stress, right, resistant to flow, right, and the friction to fluid flow. So that's why your velocity in x direction here is equals to 0. Okay, so and that's this section here is where we call it as Vx equals to 0, right? So which means if you denote here as the pipe wall here, right, as r equals to r, while this section here, you can denote it as the pipe wall r equals to negative r. So at both this boundary here, this one and this one, your Vx will also be 0 because of the viscous effect, or it is also known as the no-slip condition, where if you look at this terminology here, fluid particles adjacent to the wall, it will adhere to the surface of the wall and hence it will move at the same velocity of the wall. So Vx is equals to 0 and r equals to positive r and negative r. Okay, so now then all right, so I've actually talked about this. So just now we talked about this one, the no slip condition. All right, so here they just repeat that. So at this one, the point of symmetry, all right, at the boundary r equals to 0. So which means this is actually the center of the pipe, right, of the pipe. So it's at a distance far away from the pipe wall. So in this case here, then the viscous effect, it should be negligible already, right? The viscous effect is negligible, right? Negligible, okay, negligible viscous effect. Right, so that's why here, all right, so your velocity, it will be velocity of the fluid, it will traveling at the maximum velocity. So you can see the magnitude of the velocity, this arrow here, right, in the velocity profile. Now, so then, okay, so this is just a summary, not repeat, right, the summary, okay. Okay, now, the next thing, all right, so let's look at the shear stress. So again, at this center of the pipe, right, when r is equal to 0, so we know that the velocity Vx is equals to Vx max, and then negligible viscous effect. So which means, so that's why this part here, right, this drawing here, that's your momentum flux profile. So so you can highlight this, right? This one is the momentum flux, or in other words, which means this is the shear stress, right? So, but most of the time you see that they use the term momentum flux profile, right? So this one here, whereas this one is, we call it the velocity profile. Okay. So hopefully, you need to get to know about the term, right? So that's why at the center, right? So you can see here at the center of pi r equals to 0 here, right? So your tau rx. So again, this is a fluid flow in x direction, all right? And the momentum or the shear stress is actually act on a plane, right? That is perpendicular to the radial direction, right? Because the momentum, so you just imagine this is the pipe, right? All right, so the fluid is flowing. So the momentum actually transfer in radial direction, right? So it's transferring in radial direction. So that's why for this plane here, so it's r, right? For cylindrical coordinates, we only have 3, which is the x, r, and theta. All right, so that's why here is tau rx. All right, so your shear stress, or we say the momentum flux here at the center of pipe, it would be equals to 0 because of negligible viscous effect. All right, so this is for the shear stress at r equals to 0. Now, how about at the pipe wall? So you can look at here. So at the boundary r equals to positive r, which is here, okay, and negative r, okay, here. So r equals to positive r equals to negative r, right? So which is this point, all right? So same thing, it's drawn in this way so that you can like illustrate the magnitude of the shear stress. It's not to denote that at this section here the shear stress is here. No, it's just a magnitude. It's just a magnitude to show the magnitude of it. All right. So then the tau rx here, it would be equals to tau rx maximum. The fluid which is just next to the wall, right? The layer of fluid that is just next to a wall, it will experience the maximum shear stress, right? Maximum resistance to flow, which is also why at this region here, that's why your Vx in x direction, right? Velocity of the fluid in x direction, it comes to a stop, 0. Okay, the no slip condition. All right, so this is a summary, all right, of the velocity profile. All right, so that's how you can draw it, right? And also the momentum flux profile here. Okay, so before I proceed to the vertical plate, the velocity profile and momentum flux profile for vertical plate, any questions so far for velocity profile of pipe flow? Anyone? Okay, all right, one thumbs up. How about others? Are you okay so far? Should be okay to imagine, right? Visualize with this drawing here, then you can visualize how the velocity profile and the velocity and the shear stress change in the pipe. All right, so good, great. Okay, so that's why here you can see it's very curvature, right? Here you have a very significant curve here because it's a laminar flow. If it's a turbulent flow, then it would be flatter here, somewhere near the center of the pipe. All right, okay. Now, so we have done this one just now for laminar flow in cylindrical pipe. So the next one, we are going to look at this case here. If we have flow past a vertical plate. So some of this case is like, for example, let's say a heat exchanger, the plate heat exchanger, you have a fluid flow down the plate, right? Or in between two plates, all right? So this would be the kind of case, right? So it could be the case also sometimes like a fluid flow down inclined plate, right? So that would be later we'll discuss some example in when we cover the Navier-Stokes equation, right? So today and for this topic we focus on more simple geometry first. All right, so now if it's for vertical plate, Same thing for laminar flow. All right. So when a liquid film flow past a plate vertically, all right. So now the first thing you need to understand the direction first. All right. So when we talk about plate, which means we are dealing with the Cartesian coordinate. All right, the Cartesian coordinate. So which means it will involve x, y, and z. Now, so usually we'll denote this one, whether it's going up or down, as the z direction, right? Oh, oops. Whether the fluid is going, flowing down or up, we'll denote that as the z direction, right? So in case here, all right. So for this case here, we are assuming that we have a fluid that flows down in flowing down, right? It's not being pumped up, so it's flowing down. Okay. And then so this direction here is the x direction, which means then for the width of the fluid flow, right? So if it's, let's say this is the width, right? So you can look at it as this is the width, then it will be in the y direction. So in the x direction, as if we are talking about the thickness, you can see here, right? So they denote here as the thickness of the film. So let's say the thickness of the film is equals to delta, right? The fluid film here. Okay, so that's the direction, the x and the z direction. So the x direction is the distance of the fluid from plate. Usually we'll denote here, this point here, at a distance far away from the plate, this point here as x equals to 0. Alright, so take note of it. So it is not we randomly assign a symbol, but if you refer to most of the reference, right, either from book or from online sources, usually for a distance far away from the plate, right, for a fluid film that flow past it, this one it will be denoted as x equals to 0. Okay, that's the boundary. While this boundary here, right, so this one will denote it as x equals to delta, right, which is equivalent to the thickness of the plate. So you can actually note it down in your lecture note if you are taking notes now. Okay, how you define the boundary, because later you need to know how to define the boundary in order to assign it to the integration. When we integrate, we will need to know what's the boundary, right, and the boundary conditions, right? So, all right. So now for this case, the fluid is flowing down in z direction. So that's why you can see here it's mentioned as the direction of flow is in z direction, and then for the distance is in x direction. All right. So now you can see from the velocity profile, this is an example of the velocity profile for fluid flow down a vertical plate. All right. So the fluid is flowing in the z direction. So that's why we are denoting it as Vz, fluid flowing down in the z direction. And the velocity, if you look at it here, the velocity, it actually varies in the x direction. So that's why Vz is a function of x, right? So why is it vary in the x direction? So let's discuss about this. So if you look at here, okay, when x is equals to 0 at this boundary here, along this boundary, x equals to 0, that's where it's a distance far away from the plate, right? So which means then the viscous effect would be negligible, right? Right? The friction to fluid flow would be negligible in this boundary here. So that's why the velocity in z direction, we will denote it as Vz max. Your fluid layer, right, the fluid molecules, it traveling at this boundary here, it would be at the maximum velocity because it's at a distance, right, distance far away from the plate, where you have negligible viscous effect or shear stress. All right, it's the same thing. Okay, so whereas if you look at this boundary here, this one, right, where is x equals to delta, equivalent to the thickness of the fluid film, right, where in this region here, so the no slip condition, right, as stated by the no slip condition, right, at the wall here, right, so your velocity in z direction, it will equals to 0, right? So according to the no slip condition, right, the fluid layer which is adjacent to the wall, it will adhere to the wall, and it will travel at the same velocity of the wall. All right, so this is the no slip condition. So, and the reason is also where in this boundary here, which is the boundary, all right, which it will experience. So this boundary here, x equals to delta, right, when v at vz, right, is equals to 0. Okay, so how do you express the shear stress? So we know that the shear stress here, it would be maximum, right? We know, although this is no slit, all right? So this is a fluid traveling in z direction. So for the flow, right, then you can denote it as the z direction. Okay, so and then you have to look at the momentum, or you can look at the forces act on a plane that is perpendicular to which direction. So let's say you just draw an imaginary plate here, all right, so as if it's an imaginary plate. So this plate here, all right, okay, or if you draw an imaginary 3D diagram, right, so this is the fluid film layer, right, well, this is the plate, right? So this fluid film layer, the shear stress, it actually, right? So this plane here is actually perpendicular to the x direction, right? If you look at it, it's perpendicular to the x direction. So that's why it's denoted as tau xz, right? Fluid flow in z direction, and the force is acting on a plane, this plane here, right? So if you look at it, this imaginary plane, right, which is perpendicular to the x direction. Right? So at this boundary here, x equals to delta. All right. So your shear stress tau xz, it would be maximum. Right. That's the boundary where the fluid layer, it will experience the maximum shear stress or friction to fluid flow. Whereas at this boundary here, which is this one, all right, that I draw in red. Okay. Let me also highlight it. There's too much of drawing here. This one that I highlight now in orange, right? So which is at x equals to 0 at a distance far away from the plate, right? So you can look at it as if that's the top layer of the fluid film, right? So that's where we know that your velocity, okay, vz here, okay, the velocity in z direction is traveling at the maximum velocity, and here the shear stress, the z-directed momentum, which is transferred in the x direction, it would be equals to 0. There's no friction to fluid flow at a distance far away from the plate. Okay, let me see. Let me check something here. At x equals to 0. Okay, yeah, it's correct. Okay, the summary here is correct. I was checking and the summary, it should be correct. Okay, now, so that's the summary for the velocity profile, right? So that's why you can see here, right? So for the velocity profile, which is this one here, the magnitude of it, it would be 0 at x equals to delta, right? No slip condition, but it would be maximum, right? So here it's maximum when it's at x equals to 0. And at the same time, because the fluid is maximum, right, the fluid velocity is maximum at x equals to 0, so your momentum flux or the shear stress here is 0, right? So it's 0. And then when it's at x equals to delta, all right, so it's at this point, the magnitude is the highest, right? So that's the momentum flux drawing, all right, momentum flux profile for, let's say, fluid flow down a vertical plate. All right. So, do you all have any questions so far for this one? For the velocity and momentum flux profile for vertical flow over a plate? Any question? Before we proceed to the next section. Let me check the chat area. Okay, seems like no. Okay. All right. Okay. Thanks for confirmation. Yeah. All right. So if no, then let's proceed. Then we'll proceed. Around until 10:55. Then I'll give a 5 minutes break where everyone to take a rest. Yeah. Okay. We'll try to do more first. Okay. Now, so the next part is, so now you are aware about the velocity profile, and actually also we also do talk about the momentum flux profile. All right. And what are the flow conditions, which mean also we call it the boundary conditions, right? So that will apply to formulate the velocity profile later. Okay. Now to formulate velocity profile, we'll need to look at the overall momentum balance and the shell balance, right? So the one that we are going to use later, right, is actually the shell balance method to solve the velocity profile. But this shell balance, it actually originates from the overall momentum balance. So what's the difference between these two? So it's about the level of at which we investigate or examine the system. So as mentioned in lecture 1, right? So when we examine the system, we can examine it at 3 levels. The macroscopic level, this one, all right? Microscopic and molecular level. So when we talk about macroscopic level is where we use all the overall balance, right? Like overall mass balance, overall energy balance, and overall momentum balance to look at what happens to the system. So the system then it will be, let's say this one, right? It's a bigger level now, higher level, where let's say overall mass balance, you're looking at what is the amount, the mass of weight that is entering the system and leaving the system, right? But when we look at the microscopic level, right? So let's say for the case of when we are analyzing momentum balance, right? So the equation that we are going to use, we call it the shell balance equation, right? So let's say we want to know exactly what happens in this region, the velocity profile, or we would like to know about the momentum flux at this region here, right? So then we are analyzing at microscopic level, right? So we are going to use shell balance. So before we talk about shell balance, let's look at what is overall momentum balance. Yeah. Now, so uh, momentum, as we know, okay, so it can be denoted by this capital letter P. So it's equals to the mass multiplied to the velocity, right? And for the mass, we know that it can be calculated using the density, right? Kilogram per meter cube multiplied to the volume. So you get back the mass. Okay, so later you see how this one expression here is used to use in the shell momentum balance and overall momentum balance equation as well. Now, so according to the Newton's second law, all right, so it says that the time rate of change of momentum. So time rate of change of momentum, which means it's equivalent to momentum flux, right? If you recall back, okay, time rate of change of momentum is equivalent to momentum flux or the shear stress, okay? So according to the Newton's second law, is equals to the summation of all forces acting on the system and take place in the direction of the net force. So what it means here is, let's say this is the region in space that you choose to analyze, all right? So the time rate of change of momentum or momentum flux, or we call it shear stress, is equivalent to all the forces that act on the system, all right, but in the direction of flow. So that's why here, the sum of forces, this is the term here that it means, sum of forces, and in the direction of the net force, which means because forces eventually, if you add it up, there will be a net direction, right? So let's say it could be Cartesian, let's say Cartesian coordinate, then it will be the sum of forces in the x direction or y or the z direction. So equals to the time rate of the change of momentum, right? So this one, the rate of change of momentum respect to time. So then we are going to look at the overall equation for this one first. What is the overall momentum balance equation? Then later we talk about what are some examples of the forces that will act on a system. Now, so this is an example of the overall momentum balance equation. Not example actually, sorry. This is the overall momentum balance equation, right? Where the sum of forces, okay, the sum of forces, so which means is this one. The sum of forces that act on a control volume is equals to the rate of momentum leaving the control volume minus the rate of momentum entering the control volume, then plus rate of accumulation of the momentum. So this is the accumulation term. So which means if it's a steady state, then this term, it will go to 0, right? So if it's a steady state. So then the sum of forces that act on the system, it will just equivalent to this one. Or sometimes they also call it as the rate of momentum efflux, right? They simplify it as the rate of momentum efflux. Now, so let's say, all right, so this is the control volume or the control surface that is being focused. And then you have a fluid flow in this direction here. it's not perpendicular. So some let's say if it's in a direction that is inclined, all right, that is normal to this symmetry here. So how they describe the rate of momentum efflux term, which is the rate of momentum leaving and entering the system, right? So it's expressed as the velocity vector multiplied to the density and velocity, which this one, if you calculate it, is equivalent to the m value. All right, and then multiplied to the area. For this area here is expressed in differential term. All right, so it's the differential of the cross-sectional area that is actually the plane, right? The cross-sectional, right, which is on a plane that is normal to the direction of the flow. Right, so that's why you can see that they take into consideration of this angle here. All right, so or here, this one here is the differential area that is projected in the normal direction to the velocity. All right, so now this term here, the raw v, this density multiplied to velocity, is also known as the mass flow rate per unit area. Okay, it has a unit like the same one as you all learned from a mass transfer. Okay, so what I described now at the moment, don't panic. You're not going to apply overall momentum balance, so don't panic. Right. So this one is to introduce to you, to let you have an idea how the equation, the shell momentum balance equation, where it come from. Right. Just an introduction. You do not need to do this. Okay. Just an introduction. The one that you need to focus, I'll highlight it later. That you need to focus. Okay. All right. So this is the rate of momentum efflux term. So before we put it into the equation, right? So uh, the net of momentum efflux for the control volume, it would be expressed in this form here. It's a double integral of the term that we discussed just now. All right. And then for the rate of accumulation, so you can see that it's a triple integral of the product of density multiplied to velocity, integrated with respect to the velocity, and the whole thing will need to calculate it with respect to the change in time. So then it will be equivalent to the sum of the force. So you can try it out. The unit eventually it will be equivalent to the force. All right. So substituting the equation, the two equation into the overall momentum balance equation. So this part of the term here expression is equivalent to the net momentum efflux, which is the rate of momentum leaving the system minus the rate of momentum entering the system. Okay, and then plus the rate of accumulation term. So as you know, most of the time, when it's the rate of accumulation term, we'll integrate it with respect to the volume, right? Then divide it by time. Okay. Now, this one is just to let you have a clearer idea. All right. So why is it expressed in this form here? V multiplied to density multiplied to the velocity. All right. So eventually it's equivalent to the force, right? Because here, if you recall back, uh, momentum is mv over time, right? So kilogram meter per second, and then divide by time. So which means for the shear stress or the momentum flux, right, it should have the unit of kilogram per meter second squared. All right. So here, if you look at it, right, so it's meter per second, right, kilogram per meter cube. Okay. So and here we have meter per second. So eventually, all right, so this will cancel out, right? So it's equivalent to kilogram per meter second square. Okay, for the term. All right. So okay, now it's the same thing, right? So to tell you that, so it's equivalent to the force. All right. So now, so for this sum of forces here, because if you recall back the Newton's second law, it mentioned that here, okay, let us look at it. The Newton's second law, right? The time rate of change of momentum, this one, dp over dt, right, is equals to the summation of all forces acting on the system that take place in the direction of the net force. So let's say if we investigate it, right, the momentum, right, according to the direction. So you see that the sum of forces, right? So it also denotes according to the direction of the flow. So if the flow is in x direction, let's say if it's in Cartesian coordinate, so you can see those vector velocity is expressed in the x direction or in y direction for sum of forces in y direction and for sum of forces in the z direction. All right. So this is the overall momentum balance equation. Okay, let me see. Okay, just maybe. Okay, I'll just cover 2 more slides, a quick one. Right, then we'll take a break. So for this sum of forces here, so sum of fx, fy, of fz. So what is included in the left-hand side of the equation when they say the rate of change of the momentum, right? Time rate of change of momentum is equal to sum of forces. So what are the forces that will act on the control volume of the system? So there are 4 types. The body force, denoted by G, right? Body force is denoted by the subscript G, and we have pressure force by subscript P, right? So this X here is just to tell us what is the direction of the fluid flow. And we have friction force, or another term for it is also the shear force, right? So it's denoted by S, and the solid surface force by the symbol Rx. So what are these forces here? So you can look at the definition here. So for the left side of the equation, the sum of forces, when we talk about body force, is caused by the gravity, right, which act on the mass of the control volume. So let's say if you have a fluid flow, right, that flows in the horizontal z direction, right? So let's say this is the z direction, right? So definitely gravity will act on this fluid flow in the z direction, right? So later when we analyze, then we'll need to take into consideration, then this will be fzg, because it's flow in z direction and it's affected by the gravitational force. But if it's the case, if it's a pipe flow and then in horizontal direction, right, in this kind of case, then the gravitational force effect on it is negligible. So that's why you can see here, you take note, right, fxg, the body force, it can be neglected if the flow is horizontal. Okay. Okay, now for the second one, if for the case of pressure force, so it's like, let's say for a fully developed region within a pipe flow, so for a fluid that flows in and out of a system, right, there's like a pressure that acts on this cross-sectional area here, right? There's a pressure force that acts on this to cause the fluid flow in and out of the system, right? So this is what they say here. It's an x-directed force. So let's say if the fluid is in x direction, right, caused by pressure force acting on the surface of the fluid. Okay, so then for friction force, so friction force, let's say if it's for the pipe flow, so it actually acts on the cylindrical body, this one here, if you look at it, because it's caused by the pipe wall, right? And also each fluid layer, when they flow past each other, there's friction and viscous effect between them as well. So when we look at the overall system, when we talk about overall momentum balance, here the friction force is used to shear or friction force exerted on the fluid by the solid wall. When it's the case of, let's say we look at the this one, the control volume, the whole system. Okay, so and the last one, the solid surface force, is the force exerted by the solid surface, the pipe wall, right, on the fluid. Okay, so these are the 4 types of forces that will act on the system. Okay, so any questions so far before we take a break? Later we'll still continue to talk about this different type of forces. Any question? Okay, so if no, I think it's better that we take a break now before we continue further, because other next few slide is we talk about formulation already. Okay, so let's take a break and come back at 11:03, right? And I will post the camp code also. Okay, it's 11:05 already. So I'll post the passcode in the chat area, yeah? Just to check, double check. Can everyone hear me? If you can hear me, okay, thanks, Doris. Okay, let me share the screen again because I'm changing from device to device, so I need to make sure that everyone can hear me. All right, let's continue. Okay. So the overall momentum balance equation, right? On the right hand side just now that you can see is the net momentum efflux, which is equivalent to the rate of momentum leaving the system minus the rate of momentum entering the system, then plus the rate of accumulation of momentum. That's the right hand side of the equation, which is equivalent to the time rate of change of the momentum. Then for that is equal to the sum of forces that act on the system. So the sum of forces is contributed by all these four types of forces: body force, pressure force, friction force, and solid surface force. Now, so let's look at this again, just a quick one. So let's say, all right, when we talk about the macroscopic level, we look at this whole control volume here, right, for a fluid flow through a channel that's changed in area. So now, then if the flow through this through this nozzle in x direction, right, and it's occurring at steady state as mentioned just now, right, the rate of accumulation, this is the rate of accumulation of momentum term, it will then be equals to zero if the flow is in steady state. Now, in this case here, if you look at this area is here, right? And the fluid flow is in the direction that is perpendicular to the cross-sectional area instead of the one just now, right? The fluid flow is inclined, all right? So if it's perpendicular, right? So cos alpha, when cos alpha is equals to 0 or equals to 180, is equals to 1, right? Plus minus 1. So that's why this term here, it will goes to 1. And you see later in the next slide, all right? So you can compare here, okay? So this term here, we also call it as the net of momentum efflux as mentioned just now, the net of rate of momentum efflux. Okay, so it's then simplified into this form here, right? Because the flow is perpendicular to the cross-sectional area. And with this, all right, so this term here, the net of momentum efflux term, it will then just simplify into this form without the cos alpha. So it will be double integration of the vector velocity vector with this one, the density multiplied to the velocity, right? Integrated with respect to the area. And so if you solve it, eventually it could be expressed as here, right? So the density multiplied to velocity multiplied to area and multiplied to the average velocity of the fluid, right? This is for the term for the rate of momentum that is leaving the control volume. So then minus the rate of momentum that is entering the control volume. Now, if you recall back, okay, so we also know that the mass flow rate, all right, is also equals to density multiplied to, this one is the volumetric flow rate, right? Volumetric flow rate, all right. And for volumetric flow rate, it can also be expressed as the area multiplied to velocity. Okay, so if we rearrange this, we can get an expression for, let me see here, we can rearrange it and get an expression for this part of the equation where the density multiplied to the cross-sectional area is equals to the mass flow rate divided by the average velocity, right? So mass flow rate is equals to rho A V, right? So let's say because most of the time we calculate the mass rate using average velocity, although you know that yes, the velocity profile, it will change, right, within the distance from the center point of the pipe. But usually when we analyze, right, or you do calculation of flow rate, we use the average velocity, the average of all the velocity throughout the cross-sectional area. All right, so rearranging this, that's why you get mass flow rate divided by the average velocity, all right, for the density multiplied to area. So substituting it into this part of the equation, all right, so that's why you can see here you have v squared, all right, v square, so the v here, right, multiplied to average velocity, you have the square of average velocity. All right, so for density and area, so it's substitute by the mass flow rate divided by the velocity, average velocity. All right, so then it can be expressed in this form now for the net momentum efflux. All right, and sometimes this v square over v here, it can be replaced by this expression, the average velocity divided by beta, which is a momentum velocity correction factor, depending on whether the flow is turbulent or if it's laminar. Okay, now, so okay, this is just an introduction, and no worries, you are not required to reproduce this one in test, okay, or final exam. It's just for your knowledge. Now, if we look at the case just now, when you have flow in a nozzle, right? So the flow in this direction, where this is the x direction, right? It denotes just now x, and this one here, it should be the radial direction, right? So the flow is horizontal, and then which means that's why here, when we look at the sum of forces, it will be in x direction. And for the left side of the equation, right, so because the flow is horizontal, right, the flow is horizontal, that's why this one, the body force, this is the body force, if you recall back, the body force for horizontal flow is equals to 0, right? So you can denote here because it's horizontal flow. Okay, so definitely we'll need to consider the pressure force, because there might be something that act on it, right, that cause the fluid to flow from this x equals to 0 to this x, this exit here. So pressure force has to be considered. Okay, and then the solid surface force is due to the wall of the nozzle, so we will consider it when we are talking about the overall momentum balance. Now, if it's a very smooth nozzle, so then this is the friction force. If the scenario is the case where you encounter a very smooth nozzle, then you can assume that the shear force to be negligible. But most of the cases, right, we will need to consider this shear force or the friction force here. Now, if this is the case, right, which means the whole equation, you can see that it will then be simplified to this form here on the left-hand side. All right, so sum of forces is only left with the pressure force and solid surface force, and then equals to this one, the net momentum efflux term. So just now there's another term, which is the rate of accumulation term, right? All right, so this one goes to 0 because of steady state already, so it's reduced already, right? So we only focus on here. Okay, as for the pressure force now, so you can express it explicitly. So now, as you know, pressure is equals to force per unit area. So when we talk about pressure force, rearranging the equation, so it will be equivalent to the pressure, right, that act on the surface multiplied to the cross-sectional area. So that's why you can see here pressure force is expressed as the pressure, right, multiplied to the cross-sectional area at point 1 minus the pressure force acts on the cross-sectional area at the exit. All right, so then substituting this into the equation and rearrange it, so you can see that the Rx, right, so the Rx is here, right, is equals to this one, the net momentum effluxant, the one that is leaving. Actually, there's an overdot. You can correct this. There should be an overdot here. It went missing when I print it out as a PDF. Okay, so there should be an overdot here, right? So same this one here, as you can see from the previous line of the equation. All right, so the solid surface force is equal to then the net momentum efflux, the rate of momentum that is leaving the system minus the rate of momentum entering the system, plus the pressure force. All right, so now this Rx here, it would be positive if it's the solid surface force that act on the fluid. But if it's the opposite direction, if it's the force exerted by the fluid on the solid, then it will take a negative value. Okay, all right. So what we discuss now is all about fluid developed flow, all right? A region which is further down from the entrance of at the upper section from the exit, where your velocity profile is fully established, and then it will remain constant throughout the fully developed region. But if it's non-fully developed region, then your the analysis for the momentum, this one, the sum of forces, then it will be more complicated. But that's not our focus. right, at this level of study so far. Okay, now, any question that you'd like to ask so far up to this point before we start to look at how to apply the shell momentum balance? Any question? So this part here is for your knowledge on the overall momentum balance. Our focus later is more on so from the overall momentum balance, how we apply it to get the velocity profile. Okay, no question, anyone? Okay, just let me have a quick check on the. Okay, 20 students. Let me check on the attendance a while. Okay, so everyone has taken the attendance. Okay, great. All right, so let's proceed with the next subtopic. All right, so now if you look at overall momentum balance for what we have discussed just now, like for the case of the flow in the nozzle, right, or when we talk about the pipe flow, what we talk about it is we are using the overall momentum balance to analyze macroscopic control volume, but it didn't tell us what happens inside. So let's say this section of the fluid that is flowing, or this section further down, right, more at microscopic level. It didn't tell us what happened inside, whether is it, let's say, the velocity, how it changed, right, from the center of the pipe to the pipe wall, or the momentum flux, how it changed, or the pressure drop as well, how it changed. So now, here, so if we want to get more detailed analysis on the velocity profile and the pressure drop in the control volume itself, we need to apply the shell momentum balance. Now, this is very similar to the overall momentum balance equation that we discussed just now. It's just that instead of the whole control volume, we shrink it to a differential size. We shrink it to the small size. We look at differential size, and then therefore, you notice just now the left side of the equation, the sum of forces, some of the term it will disappear. One of the term it will disappear. Okay, so now let's look at the shell momentum balance. Now, what do we mean by shrink it to differential size, right? To apply the shell momentum balance to get eventually the velocity profile and also, let's say, the momentum flux profile. So it's like this. Let's say, all right, this one here is your pipe wall. Okay, let's say this is the pipe wall, all right, and it has a radius, all right, an inner radius of, oh, okay, it's written here, of r, and then here is the boundary r equals to 0. This boundary here, all right, is r equals to r. Okay, now when we analyze at microscopic level, so as you know, right, when fluid flows in a pipe, all right, so the momentum actually transfer in radial direction. And also, if you recall back, when this is a pipe flow, the velocity profile, it looks like this, all right, so which means the layer of fluid is like when the velocity change, right, is actually in ring form, right? This ring, it travels if it's closer to the, let me see. Let's say this one, all right, if you visualize this as a cylindrical layer, you can look at the video. Okay, if this is a cylindrical layer, okay, the one that is closer to the center of a pipe, it will travel even at a higher velocity. Then when it's the radius, all right, the radius is even larger, right, so more distant from the center of pipe, then this layer of fluid, it will travel at a slower velocity. So that's why when you shrink it to a differential size, you see that we are actually analyzing a ring of the flow, right? A very differential size here, right, within the fluid, all right? And for this ring here of flow, right, the differential size, so the boundary, we denote it as this one, the thickness of the ring is delta x, right? And here, this one, the thickness in let's say the x direction, right, the thickness of this ring here is delta r. Okay, so that's how we denote it. Okay, so usually this boundary, then we'll say this as this is x, and then this boundary on the right hand side is x plus delta x, right? Well, this one, then at the inner of the ring, then it will be denoted as R. The boundary is R. And this one, it will be denoted as R plus delta R. Okay. Now, so, okay, I'll not elaborate further first because we'll need to talk about something. So this one is just a quick introduction on how you shrink the control volume to a differential size. So we will be analyzing the velocity, we will be formulating the velocity profile using shell momentum balance according to this cross-section area here. All right. So now, eventually, when we get the equation, the Vx equation is known as the Hagen-Poiseuille equation for fluid flow in pipe. And we are analyzing for the case of laminar flow, for fluid flow at steady state, so which means the rate of accumulation term is equal to 0, and it's one-dimensional, which means the fluid flow, so in that case, it's a horizontal pipe flow right just now here. So this is the x direction. This is the radial direction. So the fluid flow in, we're looking at fluid flow in just one direction, fluid flow in the x direction. Okay, and we are looking at the fully developed region. Let's say if it's a very long pipe, right, the fully developed region, which means somewhere here, right, further down the exit, and then far away from, further down the entrance, right, somewhere upper from the exit. So this is the fully developed flow region. We call it the fully developed flow region, where your velocity profile in this region, it will be of the same shape, because as mentioned just now, let's say along this center line here, or along any distance from the radial direction, your velocity at this region V1, it will be equals to velocity at this part here, V2. That's what we call it the fully developed region. All right. So now the velocity profile, it will be affected by a few things. When we formulate it, we'll need to consider the geometry that we are dealing with, whether it's horizontal or whether it's vertical, or sometimes if it's inclined. All right. And also, what are the forces, right? What are the forces that act on the fluid flow? Okay, and the boundary conditions that we have discussed during the first hour of the lecture. All right, and to do that, all right, so later you'll see we'll need to make some assumption. All right, so we'll come back to this later. All right, so we'll look at this one first. Okay, how we denote the things here. Okay. Okay, this is a long lecture and it's quite challenging one. Now, so as mentioned, this is the region boundary x, right? And then this is the boundary x plus delta x. And here is the inner radius, we denote it as r, and this is r plus delta r. So that's why you can see. So when we are analyzing this differential size here, okay, this ring of fluid, right, this layer of fluid, that is differential size layer of fluid that is traveling in the x direction. So for fluid flow, in this case, there will be pressure that acts on it, right? So if you look at it, it's actually act on this surface area, this one, the ring. Okay, this is the one. The pressure force will act on this surface area, right? This would be the pressure force, and you can see how they denote it. All right, for pressure force that act on this boundary x here, right, is denoted as the pressure force acted on the boundary x, right? So you have a bar and x here. While at the other surface of the ring, this one here, for pressure force that is leaving this boundary here, is denoted as the pressure force, right, at the boundary x plus delta x. Okay, now, so let's look at some of the assumptions. There are a few assumptions that we will make when we are going to formulate the velocity profile. All right, so first one is related to the direction of flow. So if the flow is in x direction, right, the fluid flow in x direction, which means the pressure also vary in that direction of flow. So which means here pressure varies in the x direction. For the case that we are discussing now, right, the pressure varies in the x direction. All right, and now we are assuming also the fluid is incompressible. When we say fluid is incompressible, which means the volume would not change, right? And then usually the mass would be constant. So if mass and volume is not changing, so that's why the density is constant, right? So most cases when we analyze fluid flow later, that you can see, we are assuming that is an incompressible fluid. All right, and also we assume that we are dealing with Newtonian fluid. Now, the reason why we do this assumption here, it also depends on the scenario that you are given. If let's say it mentioned that it's a water or a vegetable oil or glycerol that is flowing in a pipe, then you know that it's a Newtonian fluid. So we need to know that whether it's a Newtonian fluid, or you make an assumption that it's a Newtonian fluid, because somewhere around the formulation, right, so it will be first expressed in the shear stress, right? But to get the velocity profile, the velocity equation, then we will need to substitute the Newtonian law of viscosity equation into it, right, to solve for the equation. Because if you recall back, right, shear stress is equals to negative mu dv dy. Let's say dvx dy. So this case here, it would then dvx dr, because the velocity change in radial direction. So by integrating this, then we will be able to get an expression. Oh, sorry. So by solving this, right, substituting the boundary, then we should be able to get an expression for the Vx, right, by substituting Newton's law of viscosity to this. So if let's say if the scenario is non-Newtonian fluid, then what you do is the same thing. You just substitute the power law equation here into the shear stress to solve it. Okay. Now, then another one, a very common assumption is the flow is steady. So which means the velocity, the pressure, and the shear stress at any point, it will remain the same over time, right? For velocity, it may not be the same over the cross-sectional area, because you know that the velocity change, right, in the radial direction. But at any time, right, along the pipe, okay, at the same distance from the center of the pipe, the velocity will remain the same. All right. So another one, which is here, right, we call it the fully developed flow. This means that the channel length, right, is much longer than the entrance length or the exit length, all right, such that your velocity profile, it will remain constant. And then we are also analyzing for the case if the flow is laminar. All right. So these are the 6 assumptions that we usually will make, all right, when we do formulation of the velocity profile. Okay. All right. So, okay. Now, before I proceed to the formulation, any questions so far about the assumption thing? Well, if it's all good, then you can give a thumbs up. I know that some of you might be exhausted already by now. There's so many new theories, new formula. Yes, Adrian, any question?
Accidentally press.
Sorry?
I accidentally press.
Oh, okay. All right, it's okay. All right, how about others? Any question? If it's okay, all good, everyone. Hang on there. All right, so a little bit more. Then, yeah, a little bit more. Okay. It is challenging for me also, because I every Monday I have 4 hours lecture. When it comes to formulation, I'm a bit dizzy now for talking too long. Just give me 1 minute. Need to take my breath. Okay, now, so for the velocity profile, okay, now, at steady state, as mentioned earlier, right? So the sum of forces, this one, the sum of forces. So in this case, the sum of forces would then be, because the fluid flow in the pipe that we mentioned just now is in x direction. So the sum of forces, it will then be denoted as this sum of forces in x direction, right? Fx. So it's equals to the rate of momentum out minus the rate of momentum in. Now, so do you notice that there's one more term here? There should be the rate of accumulation term, right? The rate of accumulation of momentum, which is equals to 0 in this case here, because just now we do this assumption that the flow is at steady state, all right? And then the right side of this equation, the right side of this equation, we can further simplify it with another assumption here that we mentioned just now. The fluid flow is fully developed, right? So which is mentioned just now here. Let me see. Here at this point, your V1, right? When the fluid flow is fully developed, the velocity at this boundary here, V let's say Vx, it will be equals to velocity at V plus delta x. So if that's the case, if you recall back the rate of momentum out, right, this one here is expressed as because mass flow rate is constant, right? So mv2 minus mv1. Okay, so if v1 and v2 is the same, right? So which means this whole term here is cancelled out. So the reason being that this is a fully developed flow. It's a fully developed flow, right? And because it's at steady state, so which means now the sum of forces, right, is equal to zero on the right hand side, right? It will be equivalent to zero. So as long as you make the two assumptions, steady state, and we are analyzing for the case of fully developed flow region, then the sum of forces at the fully developed region is equal to zero. This always apply for this module. All right. So what we will need to do next, right, before we can get the Vx equation now, is this part here that we will need to analyze and express explicitly. So now, for one-dimensional fluid flow in the x direction, all right. So now, for sum of forces, we have the body force. If you recall back, body force, pressure force, shear force, right? The shear force and the solid surface force. Now, okay, why the two terms are being that you see on the screen are being cancelled out? So if the fluid is flowing in the x direction, right? This is horizontal flow then, right? So if it's an horizontal flow, which means the gravitational force, it will not be accounted then. It will be negligible. Unless if it's a vertical flow, either in downward z direction or in upward, then we'll need to consider fxg, right? So in this case, it's zero because it's a horizontal flow. We can note it down, okay? And then we will assume that the solid surface force is equal to zero because we are analyzing at differential size, all right? So because solid surface force is a force that is exerted on the fluid by the wall of the pipe, right? So since you are analyzing differential size, it's far away from the pipe, okay? So that's why the Rx is equal to zero. But you would have the pressure force, right? So as you can see, the ring that we analyzed just now, right, the differential size, there will be pressure force that acts on here, Fp, right, Fxp, and then there would be shear force, right, that act on the cylindrical body of the ring, right? So this one is the cross-sectional area at which the force will act on. So for shear force is actually in radial direction, right? So this is the Fxx, right? Because in this case, then the shear force is due to the friction that caused by each fluid layer that flow past each other. So that's why you need to consider the shear force. Okay, so which means then if you rearrange the equation, right? So your sum of forces, yes, is equal to zero, and then it's only pressure force and the shear force that would be in place in this case here. All right. Then now, how do we express each of this Fxp? So how do we express each of this term here on the left hand side? So now, this is what I mentioned just now, where you will need to formulate the velocity profile from scratch, right? Where you analyze here, example here, what are the forces, right? What are the forces that act on the differential size, control volume, and then for each of it, you need to express the term explicitly, okay? Now, for pressure force, okay, pressure force. Now, as you know, pressure is force per unit area, all right? So rearranging it, the force is equals to pressure multiplied to area, okay? Now, then if you look at the ring, right, the differential size, right, the ring, the pressure force you need to know the pressure force here, it act on which cross-sectional area so that you can express the correct equation, right, for the term. For pressure force and the shear force, the cross-sectional area, which is perpendicular to the force, is different, all right? So which is what I keep drawing just now. This one. This would be the cross-sectional area. If you still couldn't visualize it, I'll show you during tutorial. Right, this ring, okay, the cross-sectional area at which the pressure force act on is this ring here, right? This ring, all right. So which is, if you look at it, is this one. It's a ring, and then for this area, it's calculated as 2 pi r, and then multiplied to delta r, because the delta r is actually this one, the thickness of this one, the ring, all right. Well, 2 pi r is actually the equation that they use to describe this circumference, right? 2 pi r multiplied to delta r, all right. So that's why, all right, for pressure force, okay, so as we said just now, the differential size, right, the ring, this boundary here is x, and this boundary here is x plus delta x, all right. So the pressure force that is entering, so you can see the pressure force entering is P multiplied pressure multiplied to the area at boundary x, right? So here, PA at boundary x, okay, minus the pressure force that act on PX, this one, another boundary, which is x plus delta x, PA, all right? And for this area, so you can see for the area, all right, the area, so it's expressed as 2 pi r delta r. Okay, so hopefully with the drawing you can imagine where the force act on. This is for pressure force. It's as if there's pressure from the fluid that is behind this differential section that push the fluid out. Right, that's the pressure force. Okay, so then another one, all right, because here we have analyzed there would be pressure force and then the shear force that act on the differential size. So for this shear force here, the same ring just now, okay, so now the area at which shear stress, so shear force or is equal, which means it's also the shear stress, right? Shear stress is where the force acts parallel to a surface, right? And for this case here, the shear force is the shear force friction that caused by the layer of fluid that is moving past each other, right? So and it's in radial direction. The shear force acts in radial direction. So that's why it's the cylindrical body. So if you look at the video that I'm showing you now, so let's say this is the cylinder, is this body here, all right? The shear force, it will act in this cross-sectional area, while pressure force acts on here. Okay, pressure force is on this ring, all right? So that's why, all right, so you know that the circumference, right, for the area, right, this is the circumference. So circumference is 2 pi r, right, and then multiplied to the length of the differential size. This would be delta x. So that's why it's multiplied to delta x. Okay, all right. And then for the boundary, in this case here, we are looking at like this. Okay. Okay, this differential size. This will be the boundary because it's acting in radial direction, right? The shear force. So it's from R to R plus delta R, the boundary, right? So that's why I can see the shear force. See, it's actually the same thing. If you look at here, this equation, all right, pressure is equals to force per unit area. Rearranging it, force is equals to pressure multiplied to area. So that's why you can see here for shear force is the shear stress. This is the shear stress. So now that's the reason why in also the first lecture you learn how to write this term here, because you need to know how to express here, knowing that the fluid is flowing in x direction, right? And then the shear stress, right, is acting on a plane that is perpendicular to the radial direction. So that's why it's expressed as tau Rx, the shear stress. And then this term here is the area. The area which is in radial where the shear stress acts in radial direction. So it's 2 pi r multiplied to delta x. All right. So it will be from the boundary r. So you can see it starts from r to r plus delta r. Okay. All right. Before I proceed to the next slide, any questions so far on how to express these two explicitly, because it's actually this part here that the student always stuck and couldn't complete the question. Because after this, once you get the expression correctly, it's just substituting it back, right? You substituted this back to here for the pressure force, and so substitute the shear stress into here. Then, yeah, we will start to simplify it and change it to differential equation. So, any questions so far? Okay, seems like no. Okay, then I'll proceed. Okay, now, so the pressure force, right? So as we discussed just now, this is the PA, right, at boundary X, and the PA at X plus delta X. Okay, because the pressure force X here, right, and then the shear force is X in radial direction. So that's why it's the shear stress tau Rx, right, at boundary R, right, and then this is the tau Rx at boundary R plus delta R. Right, what you need to take note is make sure you know how to express the area, right? Knowing that it's what is the cross-sectional area that involved and how to express the shear stress. Okay, now, so substituting back to the equation just now, because from the start, as we mentioned, right, is equals to 0, right? Because the net momentum efflux is equals to 0 because of fully developed flow, and the rate of accumulation is equals to 0 because it's steady state. And we've analyzed that for the sum of forces is only the pressure force and the shear force that will be in place, right? Then expressing each of the term explicitly. And the next thing is we rearrange it, right? So by rearranging, so we'll rearrange the shear stress here to the right hand side, so which is what you see here. So the shear force at R plus delta R minus the one that is at boundary R, equivalent to this one, the pressure force at X minus the pressure force at X plus delta X. Now to get to here, okay, so usually what we'll do, we'll need to consider what are the common terms. So you can see on both sides of the equation, you have 2 pi, 2 pi, 2 pi, and 2 pi. Now, so we have 2 pi, but then how to simplify it further? So the tricky part is with this one that the student always will feel lost. We should divide it by what common term? Now, one way to understand this, why do we divide it by 2 pi delta r, delta x delta r? For 2 pi, I think you should understand because you have 2 pi on both sides. But why do we divide by delta x and delta r? So now the reason being, so if you look at here, your pressure, all right, so your pressure, if you vary in the this one, so the fluid is flow in the x direction, which means the pressure gradient, right, it will occurs in the x direction, right? The pressure gradient, it will occurs in the x direction. So that's why here we will need to divide by delta x, so that later on the next line you have an expression where you get the delta p, right, divided by delta x. Okay, all right, okay. Now, as for the shear stress, as you know, the shear stress, when we draw the momentum flux profile, right? This is the radius of the pipe. So you can see that the momentum flux or the shear stress, it varies with the distance, right, from the center of the pipe, where you have maximum shear stress at R equals to the radius of this one. And then the shear stress here, tau Rx is equals to 0. Let's say this is the x direction. So which means your shear stress, it varies in the radial direction, right? The shear stress. Okay, I'll write here. Shear stress, it varies in radial direction. So that's why we divide it by delta R here. Okay, so that's the reason why we divide by 2 pi delta x delta R, all right? So that we can get an expression on the next line, right? So take note on this, you need to learn, you need to really master this part here. What's the common term that you need to divide, all right? So now, if you can see, okay, let me clear this, because I'll need to write something on the previous equation. Okay, so that's why if you look at here, if you divide both sides by 2 pi delta x delta r, 2 pi delta x delta r, okay, so 2 pi, 2 pi, 2 pi will cancel out, all right, and then you have delta x here, okay, the delta x, it will be cancelled out, and you have delta r on the right hand side, okay, so it will be cancelled out. All right, so that's why you can see that on the left hand side you will left with the tau rx and the r term, rx and the r term, right, which is what you get here at the boundary r plus delta r minus the tau rx r, right, at boundary r, and divided by delta r. While for the right hand side you have to be careful, right, you still have this radius term here multiplied to the pressure, radius multiplied to pressure divided by delta x. Okay, so with this, right, so whenever you see this, which means it's related to differential equation already, right? But before we assume that delta r and delta x, it will approach 0 so that we can express it in terms of differential equation, all right, so we'll need to treat this, all right. So now for a fully developed flow, because you know that for a fully developed flow, your velocity profile is actually constant in the fully developed flow, such that your V1 is here and V2 here is the same, right? So which means if fully developed flow, right, V1 equals to V2, which means your pressure gradient, it would be constant as well, right? So if the pressure gradient is constant, so this expression here, we can then rewrite it as delta P over L, right? The pressure drop, so the delta P here is, we call it the pressure drop over the length of the pipe, all right? And then by taking delta R to approach 0 and delta X to approach, so delta X here, we are not going to treat it because this section of the equation is being re-expressed as the pressure gradient, right? It's a constant value. So take note that this is a constant, right? It's a constant. While this R here, so don't be very careful. This is the part that the student always miss out, right? Forgotten to right, carry the R over the next step, right? So it's a variable, right? So we'll need to integrate it, right? As for the left hand side, you can see here, okay, so it's then decreased to the differential of the R tau rx respect to the radius. Okay, all right, now on this step, please make sure you don't like cancel out these two. You shouldn't do that. It's wrong because they are of different level. This one is R, but this is the differential of R tau Rx. They are not on the same level. So what you need to do is actually to rearrange the variable and then integrate them first. All right, so you can see on the left hand side, you are integrating respect to R tau Rx. While on the right hand side, since this is a constant, so we can just factor it out, and then we'll focus on integration of the radius with respect to R, right? So then integrating it, so R integrated, we'll get R squared over 2, right? Then plus C1, a constant value, right? So while integrating the left hand side, so it's as if we are integrating a constant 1 respect to R tau Rx, so you get this term here, okay? Then only on the next step, you can cross out each of this R here, all right? So you have to be very careful here, okay? When do not cross out those common terms when, let's say, if it's at differential form, okay? So now by this, then simplifying, so you divide R on both sides, right? So you have simplified in this manner here, where the shear stress is equals to the pressure gradient, constant pressure gradient, multiplied to R over 2 plus C1 over R. Okay, so before we proceed further, we'll need to solve this C1 here. So if you recall back, all right, so at R equals to 0, that's where the shear stress would be 0, right? The shear stress is 0 because the viscous effect is negligible. There's no friction to fluid flow. So if that's the case, so now let me proceed to here. So when R is equal to 0, tau Rx is equal to 0, So you can imagine that this when it's 0, and then when this goes to 0, which means C1 it would be equals to 0. Okay, so you have to, so this is the first boundary condition that you apply, right? So that's why I mentioned you need to know the boundary condition, the flow condition, so that you need to apply it to solve for some unknown constant after you have integrate the differential equation. All right, so substituting the boundary condition, this one, so then the equation, it will be simplified to tau Rx equals to delta P over L R over 2, which this equation here is the momentum flux. So you have obtained the first equation, the momentum flux profile, the equation that will describe the momentum flux. And if you look at here, all right, it's a linear equation, right? The shear stress, it will vary proportionally with the radius, which is what you see when we draw the momentum flux profile. It's a linear line, right? It's a linear line. So this is the momentum flux profile. Now, but this is in shear stress. What we want, if let's say is we want the expression for the velocity profile, Vx, right? So we want this one. We want the equation that express the velocity profile Vx. So what we do now, the tau Rx here, so that's the reason why in the assumption just now we make, let's say if we deal with water, glycerol or vegetable oil, right, then we will be applying the Newton law of viscosity, knowing that tau Rx, right, is equals to negative mu. The velocity Vx will change in the radial direction, right, dVx dr, because if you recall back, this is the x direction, this is the radial direction. All right, so that's why it's dVx dr. So substituting the Newton law of viscosity, then we can proceed to solve this further. All right, now as you know, viscosity is a constant value. All right, so I'll do a quick rearrangement now. So it will then be dVx dr is equals to negative pressure, the change in pressure, the pressure drop, right, divided by mu L and R over 2, right? Then we rearrange the variable. So all these, the pressure drop, viscosity, and the length of pipe is a constant value, right? So if you want to, yeah, you can actually factor out the 2, or it's also fine if we proceed like this, right? Okay, so we integrate it, then we'll get Vx negative pressure drop divided by mu L. All right, so here we'll get R squared over 4, right? R squared over 4 plus C2. Okay, but this is only the general velocity profile, right? We will need to solve for the C by substituting another boundary condition. So that is, we can substitute the boundary condition, the second one. Let's say for a case, usually we'll substitute, let's say the one which is equals to 0. So we know that the velocity is equals to 0, right? The Vx in the pipe flow, it will be equals to 0 when R is equals to the radius of the pipe wall, at the pipe wall. So then by substituting that, okay, so okay, 0, all right, so you look at this equation, all right, so substituting it, delta P over mu L, all right, and then R squared over 4 plus C2, which means your C2 is equals to delta P over mu L R squared over 4, right? So now with this, then we can substitute it back here. So your velocity profile, Vx, okay, it would then be equals to negative delta P over mu L, the small r squared, minus 4. So this r here is a variable, okay, plus C2, delta P over mu L, the big R squared, the radius of the pipe, inner radius of the pipe divided by 4. So you have some common terms here which we can factor it out. So if you factor out, it's delta P over 4 mu L, okay, you can write it as R squared minus the small r squared. Or you can further factor it out, okay, so it will be delta P 4 mu L. So I factor out the r squared since it's the inner radius of the pipe is a constant value. We factor it out, so which means it's 1 minus r This one, 1 minus the small r divided by the big R, the whole thing to the square. Okay, so it can be re-expressed in this final form here, which if you look at here, so you have an r squared. So that's why your velocity profile is of a parabolic shape, right? So this is the equation, right? Or this one is okay also to stop here, right? The equation that you can use to describe the velocity profile for a pipe flow. If you substitute r equals to some value, right, then you will be able to get the velocity at that radius. Okay. Now, just a quick one for the last two slides. So this is about the Vx. So we have get the velocity profile, the momentum flux profile, and sometimes it's useful also that we will calculate the average velocity. So for the average velocity, then what we'll need to do is the double integration of the velocity profile, this one. All right, you need to substitute here. All right, integrate it with respect to area, and then divide it by the cross-sectional area, where the cross-sectional area, because the fluid is flowing in a pipe, right, this one would be the cross-sectional area that is perpendicular to the direction of flow. So that's why it's pi r squared. And then for dA here, how they express it is expressed as this dA here, take note, is expressed as r dr d theta. All right. So when we start to integrate, we integrate from the outermost, this section here. So, and then, so because the whole thing, then it will be 2 pi. So that's why you can see integrating with respect to theta, right? So you get a 2 pi here. Okay. And then take note of the boundary also from 0 to the inner radius of the pipe. Okay. So we won't have time to cover this one. It would be good that you try it out. You try it out how to integrate it, which eventually you get this answer here for the velocity profile for the average velocity, which this is also the Hagen-Poiseuille equation that tells the relationship between the average velocity and the pressure drop. Okay, so this is the Hagen-Poiseuille equation. So you can take some time, right? Please practice, okay, practice it so that if you have time, you practice it, try it out. If you have question on how to do this, you can ask me tomorrow. Because the one that we are going to practice tomorrow is we are going to try out the average velocity for fluid flow down a vertical plate, right? We will do that case, but not this one. So you have to practice it, okay? So now another thing, if let's say, all right, if let's say this is the velocity profile that we get, right, and if we want to get an expression for the maximum velocity, so Vx is equals to Vx max when r is equals to 0, right, which is at the center of the pipe, right, which is at the center of the pipe. This section here is the Vx max. So which means you substitute this one equals to 0, the whole equation it then fall back to this section here, right, which Vx max, right, substituting Vx max, r equals to 0, you get the pressure drop divided by 4 mu L multiplied to the inner radius of the pipe. Depends on the question. There's a question in the chat area, do you always need to derive the equation? For this module, there are two ways to derive the velocity profile, as mentioned, the shell momentum balance method and the Navier-Stokes equation method. So for both, students has to master it. You have to master it. Okay, all right. So I'll stop here. You will be saturated already. I'm a bit dizzy already. Also talking so many things, so theoretical things. I have a class later at 12 again. Now, so we have covered the velocity profile, right, for pipe flow, a flow past a plate, and now we look at the different boundary conditions, and we have talked about the overall momentum balance and the shell balance method, right? The difference is this one we will consider the Rx, the solid surface force, but when we talk about differential size, right, the solid surface force is goes to 0. Okay, now I think I need to release you also because you may have class at 12, right? So thank you so much for bearing with me today. If you have any question, you note it down. Tomorrow when we have class 4 to 6, right, we'll focus on the tutorial first, and then as we discuss the question, you can ask me if you have any question, and then or even after the class. Okay, all right. So thank you very much, and so sorry I have to leave now for another lecture. Right, you note down your question, and I'll answer it tomorrow. Thank you, everyone, and I will also post the pre-recorded video. Then, if any question, you can replay back to chat. Okay. All right. Thank you. Thank you, everyone.